Hey guys, Joe Pye here at Advanced Innovations. Welcome back to the shop. Going to start this video with a shout out to the crew at Free State Beer in Lawrence, Kansas. Recently had a chance to try some of their product and scored this awesome long sleeve shirt that I can use when I ride my bike, which is going to work out really well. So hey to Eric, thank you to everybody that made that possible. That was a nice surprise. Today's video is going to be about what I like to call shear and smear. Stick with me. If you've ever got a piece of plate from a big shear, it's really not hard to tell what side was up. And this is a perfect example of where I'm headed with this. So let me illustrate that for you. Here's your die in your machine. Here's the bottom die of your machine. The material is hanging out. Leslie, here's the top punch coming down for you. Gonna shear that off. Boom. From the impact, and you would think that steel is hard, steel isn't going to smear, isn't going to push, isn't going to bend. Well, burr on a piece of metal is a living proof that steel does move. It flows, it migrates, when that shear comes down and hits the top of that part, naturally this part is going to end up dropping off down here. Life is good. But what ends up happening, and I'll see if I can do this nicely. And if we have any sheet metal guys out there, I would really appreciate you to put the exact spec for what I'm about to say in the comment line to share with everybody else. I believe it's 2/3 shear, 1/3 break. What does that mean? All right, well, here's what that means. As that shear comes down into this part, it makes a nice clean cut in about the top 2/3 of that material before the remaining cross section can't handle the load from the upper shear. And we're just going to make that real ugly. And that side decides to break off. So there's your 2/3 shear, 1/3 break. And when you look at the end of the part, you can see what looks like a shiny chrome line or a polish line or a machine line. And below that, it's like the surface of the sidewalk outside. So what's that all about? Top part got cut, bottom part broke off. Still relatively in line because of the construction of the die. You also get a very slight rolled edge on the top of the part from the pressure of the die. Boom. You can see this if you ever pick up a plate. Just look at it. You can see it perfectly. Now, I'm going to call this the shear side because it took the initial chunk, took the initial knife blade, and there it is. You're digging in. You're sheared. You have sufficient material to back it up. And on the bottom, I'm going to call the bottom the smear side. Because when you get this die out of the picture and you get this piece back from the vendor, you may have a little hook on the bottom where it pushed it, it displaced it. Same thing happens with an end mill when you're running an end mill around a part. And this is really obvious when you're doing the edge of a part, perimeter of a part, a tower, whatever. Conventional cutting versus climb cutting will absolutely create different kinds of burrs and very predictable burrs, which is good if you're a CNC guy, manual guy as well. I mean, you don't like to file burrs, right? So don't make burrs. The concept that I want to show you is a way to predict or anticipate or know ahead of time where the burrs on your part are going to be based on cutter rotation and trajectory. Doesn't matter if it's a CNC or a manual machine, but especially for a CNC, you don't want to make a part that took, hey look, this took me 2 minutes to make, and then you got to sit there for 4 minutes and deburr it. So where's the win? You want to sit there for 5 seconds and deburr it if you want to deburr it at all. So think ahead. What I'm about to show you, I'm going to walk out, I'm going to take a cutter, I'm going to run around a piece of aluminum, just because it's soft and it won't take any time, and then I'm going to do the same thing on a piece of acrylic. And we're going to try to smash that acrylic up and crater it and bust it and blow the edges off of it. I'm going to do the exact same procedure with a different type of cutter. Now, if you've watched my fly cutter video, look in the catalog below in the videos. Specific grinds on specific tools change up the stress on a part as you cut it, and it can really help you to not make a burr. Well, not only the tool geometry, but the approach that you take when you cut that part will also be vital to creating a cleaner part and a part that's faster to deburr. So let's take a walk out to the mill, throw some aluminum in the vise, cut it up. All right, first demonstration I'm going to do is we're going to deck the top of this piece of aluminum off. And this is about 1 inch by 1.5 inches, 6061. That's a 2-flute carbide 7/16 diameter end mill. And I am going to make sure that I conventional cut the entire perimeter of this part, and then we'll clean up the face. Now I'm conventional cutting the outside of this strictly to force this cutter as it comes around. All the shearing action is going to be inside the material. And as the cutter breaks through to the outside, very much like what I just did on the board inside, when this cutter comes around and gets to the outside, the material is going to want to come this way. And we're going to end up with a really ugly burr all the way around the perimeter of this part for having done this. So let's fire up this machine. I'll go about 100 thou deep. It doesn't have to be deep to make a point. And we'll see what happens. Check it out. All right, that is a full conventional cut perimeter. That is not a way I would ever cut that part. Let's take it out, pop it on the bench for a second, take a look at the burr on the edge. All right, now that is the edge. See how the material has flowed out? Right here. And believe me, that's like a razor blade, so we're not going to run our fingers across that. Get that in focus for you so you can see it. That is because the rotation of the cutter was forcing the material this way. It was smearing it outward. Now to control that burr, I'm going to replicate this exact same cut. 100 thou deep. I'm going to do the entire perimeter, but I'm going to run it in the opposite direction. I'm going to put the shearing action on the outside and push the burr to the inside where there's sufficient material that it will continue to shear it off. And if all goes well, when I pull this piece out and we come back over to this camera angle, this little raised edge right here, which is a fairly aggressive burr, not something you'd want to see come out of a production machine. Hopefully the change in direction will make that burr go completely away. If not completely away, it'll reduce it to the point where it would not take nearly the effort to eradicate, and could probably be done in a tumbler in considerably less time if that's the automated process that you used. So let's take a look. We'll put it back in the mill, go around this way, and make that burr go away. No burrs, just by changing the cut. Let's take a look at that exact cut going in the opposite direction. Depending on whether you're below or above center when you get to the corner, you have seen me do this in other videos, I will walk my cutter off and come around that corner to guarantee there's no burr on that edge or a minimal burr. That would be a climb cut perimeter. Let's take it over to the bench, compare the edge. Okay, we're going to see this for the first time together. And I think you can see clearly the burr is reduced. Now right on the corner where the cutter pushes through, you are going to see something. With the size of that burr, you can almost not feel it. Always check it with a fingernail or a scale. If you can hook it, then you better file it. But it's a much cleaner edge when you do that. Much cleaner. Although I don't like using a cutter to walk around a surface like that, if you have to do it, make sure that you're climbing into the surface and driving the burrs into the part and not off the shelf, okay? Let's do this with a piece of acrylic, and I'm going to show you the impact that this has on a piece of acrylic. It is absolutely going to detonate the plastic, and then we're going to put a different tool in, do the same thing, and see if we can clean it up. Back to the mill. Now, no demonstration on controlling burrs would be complete without showing how to handle vertical burrs as well. I'm going to take this cutter and I'm going to form two square protrusions on the top of this part about 300 deep. I'm going to climb cut the entire operation on both of them. Now when you climb cut, all the burrs shoot from behind the cutter if you're going this way. So we're going to end up with a part that has three very distinct burrs, and when we form the fourth side of the tower, the cutter is going to remove the very first side burr, and that's why you're only going to have burrs at 3 locations and not 4 on a square part. Now, I will show you that pretty clearly here, and then I'm going to show you how to make them go away without having to sit at the bench and file them. And for all you CNC guys, this is an outstanding solution to a big problem that could save you tons of money, and trust me, I've seen it have tremendous impact on production. So here we go. 300 deep. The entire operation will be climb cut with the exception of the initial channel cut down the center of this part. The burr that you just saw pop out this side, there should be a burr in the exact same location on the tower that's about to form, because that's going to be the trailing edge of the climb cut. I'm going to move this 50 thou off center, and I'm going to start to make that tower. Exactly 50 on my digital readout is where I am sitting right now. I'm going to go to, let's say, 350. Say 350 on this side as well. Same thing on the next tower. Okay, now this pass right here that I'm about to make is the reason that vertical towers only have a burr on 3 corners. When I come back through here, I'm going to remove the burr that's currently on this tower, this edge, right there. So when this cutter passes through, the burr that's shot back from the climb operation will go away. This corner will be clean. Alright, now here's the problem for all you production guys. Or even for you non-production guys, you have 300 of these things to do, and now you have 6 sharp corners that you need to worry about post-production. What is the fastest way to get rid of those burrs? Questions? Thoughts? All right, well, the fastest way to get rid of those burrs is to change your feed rate and your RPM and run that entire track all over again. Let's look at the logic there. The burrs on these parts, or in these towers, are present on this corner, and this corner, as well as here, here, and here. When you run back across that part, since the burr is hanging out this way, the cutter pulls it in and shears it off. Same thing over here. The burr is hanging out that way, so the cutter is going to pull it in and shear it off. Fastest way to deburr that part, the fastest way to deburr that part, is to run that trajectory 100% all over again, dead pass, and the burrs go with it. Let's prove that and move this part to the bench and take a look. Any remaining burrs will be vertical across the top surface, which is easily chamfered or removed. They should be minimal at best. I will start from where I was just to be fair. And also, to answer your questions, yes, you may see chips fly on this particular pass, and that would be because we have a different load on the cutter. The cutter is going to be at almost a 0 flex condition because it's really not going to be cutting anything. It's just going to be hanging out and spinning. So you will see burrs come off. They could be small, they may be dust, they may be extremely small shards, but I expect to see burrs. Chips, excuse me, not burrs. Okay, let's blow it off, take it over to the bench, see how clean they are. That second pass was exactly the same values as the first pass, and any of this small debris that you see laying around is remnant cutter flex. Those corners should be very close to being perfect. Let's find out. All right, let's take a look at the corners. This is a toothbrush, nylon toothbrush. Actually, it's a nylon toothbrush that I use for parts. It's not a toothbrush. Let's see if it takes to get them burrs off of there. I tell you, if I'm going to leave burrs on a part, I want burrs that come off with a toothbrush. That is absolutely beautiful. This corner right here has got a little visible. Let's see if that's fingernail worthy. Coming right off. To the touch, the corners are razor sharp. There is a very slight trailing edge remnant left. Ever so slight. You would still have to file these, of course, if you were going to pass this on to somebody. There's a better angle. There you go. Get the reflection out of there. See it right down in here. On. Running around the perimeter of the part again makes a world of difference. I'm surprised to see even that, to be perfectly honest with you. I'm surprised to see even that. This corner here is a little heavier than I would have anticipated. But you can see from a raw machine part, if this was a steel part and you had 100 of these on the face of one particular part, running back through it is going to be a whole lot quicker than going in there and trying to do anything else. Unless, of course, you got a corner rounding interpolation in your CNC program, but guys on manual mills don't have that luxury. So if you're doing this manually, run around it twice, knock that burr off. Let's move on to some plexiglass and try to destroy that. I'll show you some tricks for that. Okay, this is a piece of 1/2-inch acrylic. This is a rather brittle material when compared to like a poly, which is a little softer. We're going to do exactly the same thing here. Go 100 thou deep, go down one side, come around a corner, come back the other side, and hopefully make an absolute mess out of this part. What I expect to see is a very nasty broken edge all along here, possibly blow this corner off, and in the back, equally nasty edge, and in the back corner here, it should crater the chunk out of that corner. So we're going to do up and back, 2 cuts, and on the next pass doing it exactly the same way, I'll leave a rib down the center, knock the rib off, and show you what it means to crater a surface, where the material actually pulls up and out of a flat surface and not a chipped edge. So let's go about a 200 deep on this just to make the point. Let's see what happens. That is absolutely the result I expected. Mild chips on the corner, leading and trailing edges are absolutely deteriorated. And in the back here, I'm going to take this camera off and pat myself on the back with the other hand. As you can see, that corner is completely gone. It blew that back corner right off, right where I said it would break off. Now we're going to run a 200 thou deep cut exactly the same way. But we're going to start in that back corner and we're going to climb all the way around. And if there are going to be any issues, what we could expect from this particular operation with a flat bottom sharp cutter like this is to see a line of fractures running down the center of this part where the 2 cuts overlap. Let's get back to 200 deep and do that in reverse. Reverse direction, not reverse rotation. So let's check it out. 200 deep. We're about halfway through. Here we go. follow the cutter. And I do expect to chip it down here as well. Right on cue. I know the edge looks hairy, but watch this. Fingernail. Best deburring tool you got when it comes to doing it right. That is a glass smooth edge, front and rear. There you go. Absolutely razor sharp smooth. And that is overhang right there. That is not chipped. Front and rear. Makes all the difference in the world. And right where I said it was going to chip in the back corner, you can see it. There you go. If you have any concerns whatsoever about blowing the parts up, you know, like this, wiping the edges off your plastic pieces, run a climb perimeter cut, and then go down the center, and then we can actually take this exploded part and we're going to move that inboard because it's going to pull the material out. That's what I call cratering. Let's do that. 200 deep. We'll walk around the perimeter and move that chip inboard. Now, if all goes well in this demonstration, we're going to have a nice sharp edge all the way around on this piece of acrylic. But we're going to move our problem right about there. Let's see how close I am to being right. 200 deep, about a third of the cutter all the way around. We're going to run right down the center from the opposite side of where the cutter is now, and we're going to blow a hole in it right where that Sharpie mark is. Stay tuned. First thing we're going to do is go 200 deep like the previous cut, and we're going to climb cut the entire perimeter to make sure that we have at the very least a nice sharp perimeter edge with no chips. I'm a little less than halfway into the body of this end mill, and I'm going to run down the back. I am shearing the material into the plastic, so all the cutting force is going inward. This will result in a nice clean edge. I'm going to walk out and around, get back around the halfway mark on the body of the cutter, and I'm going to do it again right here. There you go. Around that cutter and back down the face of it. So this assures that I have a very clean perimeter, something that's got no chips and would be easy to file or run across some very smooth emery. Now when you do it this way, the island that's remaining in the center, the danger is that as the cutter traverses the full length of it, the very last remaining remnant is going to be taller than it is in contact with the surface that you just formed. When that happens, the end mill will make its cut and get down around the end and then blow the end right off. Right about where that black dot is, we can expect to see a crater going subsurface to this part. So we are chasing our tail here with problems and solutions. But let's see how close I am to being spot on with where that Sharpie mark is versus where the crater is formed. .200 deep, 7/16 2-flute carbide end mill. It's running about 1300 RPM here. Should be running twice that, but all right. As we get closer to the end, it's taller than it is wide, and boom, there it is. That's the explosion you can expect. And we will blow it off, power down for safety, and let's move the camera around, and I will show you the hole right on cue, guys. Right where I said it was going to be. Okay, so now we have a nice clean perimeter, but now we have craters in the surface of the part. If you are very close to net shape, a crater like that can be a real moment where you just have to push back from the machine and go get another cup of coffee because it just ruined your day.
And there's only one thing that you can do to avoid craters in parts like that, and that is to change the load when it comes time for the part to pull out. And there's the cutter is the problem. So we have to change the cutter. We're going to move over to a cutter that has a different lower profile, very much like the fly cutter that we put an angle on. We're going to do the same thing to this end mill. And if the planet's lined up, everything should go well, and that surface crater should go away. Let's change the cutter.
And here is what I have to believe is the solution to the problem. This is a 5/8 end mill that I've put about a 200 chamfer on by hand. I actually just ground that on by hand. We're going to do this exactly the same way as we did the other one. And hopefully, the chamfer being what it is, will gradually reduce the height of any obstacles and reduce the stress and not result in the crater that we have on this part right here. So let's run this one around the edge. I'm going to go 200 deep just to keep things fair. Let's see what happens. Chamfer should do the trick. Okay, we have a V-shaped remnant running down the back of this part. Let's see if we can get a profile on that for you. With a gradual incline at both ends. Back down the middle, cutting from left to right this time, just because of the camera angle. Let's see what we get. Go back and get what the cutter didn't pick up. I think this one is worthy of taking over to the bench, and we will see together what we got. Okay, we have two very small dimples in there. This is a very brittle material. I would say overall, enormous improvement in the process. Corners are sharp, edges are sharp. And those shiny spots right there, I hate to see them show up, but you gotta have to be honest with the video, right? That is about 10 thou deep, if I had to say so. It's very superficial. And that is something that could probably have been controlled with a higher RPM and a correct feed rate instead of just cranking on it. But I wanted to show the difference in the tool performance. So there you go. I think it's plenty clear to see. There's a beautiful edge. And if you control your rotation of your cutter, understand which way the shear and the smear are going to perform for you, well, you're going to spend less time with a file in your hand. Just because I very rarely settle for anything that's not 100% perfect, I went back in there at a higher RPM, same 200 deep, and I babied the feed rate. Not a speck on that. That is absolutely beautiful. Edges are good because of the little bump out at the corner. And the compressor's on, so I hope you can still hear me. Didn't blow the edges off, didn't blow the corners off, did not crater the surface. Chamfering the tool on a harder plastic like this is the way to go.
Now we're done. Thanks for watching.